Yeah, so thank you all so much for having me. I'm really excited to be here, and like very excited to get a chance to present to y'all. At some point, I should figure out what department I'm actually in, because that is not what I had in my bio. I'm here. I'm a new faculty at NYU, and I'm really excited to have a chance to talk to y'all about some of the work we've been doing in multi-agent learning for like transportation systems and autonomous vehicles and so on. The main focus of this talk is going to be about the challenge of using simulators as a guide towards the deployment of a multi-agent system. So simulators hard enough in the single agent setting. In the multi-agent setting, where you have to think about what are the actors that I'm designing my system against, things become even worse and more complicated. And to kind of, as a lead into that, I want to talk about some of the work we did in deploying an RL-based system onto the roadway that was very much guided by simulator design, and like kind of highlight some of the challenges we found and how that has led into the type of research that we do now, and like why I think these are real problems. So about 5 years ago, we had kind of this harebrained idea that we would design controllers with RL, put them on cars, put them on the roadway, and somehow make traffic better. And in particular, we were interested in trying to smooth out stop and go waves. So if you've ever been in a car, and I imagine most of you have, you've seen stop and go waves, you've sat in one, you've experienced one. And the thing is, they're quite fuel consumptive because you accelerate, you decelerate, you accelerate, you decelerate, and each of those steps kind of cuts out more fuel than if you were just smoothly moving at a low speed. So our idea was, there are all these cruise controllers on the roadway now. In like 2017 in Palo Alto, I did like a hand count, and like 4% of the cars were Teslas. And now that's a Palo Alto thing. But now most car companies have some kind of level 2, level 3 autonomous car that can keep lane distance to the car in front of it, and that can decide when it lane changes. And so that in some sense is a choice, right? You're picking how it should follow the car in front of it. And you can pick out different strategies that have different impacts on transportation systems. And so our idea was, we're going to design some cruise controllers that optimize the fuel model, so that are like kind of drive optimally with respect to a calibrated model of the car, and also smooth out these shockwaves. And we actually deployed these onto 100 vehicles in Vanderbilt in Nashville, Tennessee, about 2 years ago. And I'm going to kind of talk a little bit about how we got there, what happened, and lead that into the rest of the work. So this is part of the Circles project, which has this long name that I don't want to say out loud. And it was part of this like gigantic consortium of a bunch of universities and companies working together to build this, because deploying 100 cars onto the road takes a lot of manpower. And kind of on the right here, we have a kind of a camera shot from some of the cameras that were collecting data during this experiment. So this is for the I-24 motion data set. And the idea is that we're going to take DeepRL, combine it with self-driving things, we're going to get energy improvements. And the way we went about this is, or the way we thought we were going to go about this, is we were going to build a digital twin of the roadway that we were going to deploy onto. We're going to plug that digital twin in some cost functions, some policy gradient algorithms, which are our favorite workhorse. That's going to output us some kind of feed-forward network. Then we're going to wrap that in some analytic safety conditions, because it's not too hard to compute what are the controls that don't crash me into the car in front of me. And then kind of loop this around and maybe put these cars into the world and do another cycle that helped us build a calibrated digital twin atop the like counterfactual changes we made. And kind of the first sign of danger is that existing simulators did not really produce realistic trajectories. So we built these like really cool models of the highway in Sumo. We spent a lot of time building them. They would have like 1,000 cars in them at any time, and 4% of that would be our controllers, and the blue cars are the ones that they see, so the cars in front of them. And when we looked at the trajectories that we would get through those simulators, they did not at all look like real-world trajectories. So this is a trajectory from a real-world drive that some poor enterprising undergraduate did. So you can see, like, red is the velocity, and blue is the distance to the leader vehicle. And you can see that over the course of just like a 10-minute drive, we're at, cruising at 18 meters, down to 10, back to 18, back to 10, back to 18, down to like 2, and so on and so forth. And like 8 minutes later, we're driving at free flow. And no amount of like fiddling with the boundary conditions in our simulator, or like changing some of the hyperparameters of the human drivers in our simulator, gave us trajectories that looked anything this complicated. So first problem, like, we're already seeing kind of some of the limitations of the parameterized driving models inside our simulator. So instead of using those driving simulators, we did some test drives for data collection. Again, a poor enterprising undergraduate would go out into the highway in congestion, and they would drive around with a radar-enabled car. We would collect their trajectory and the trajectory of the car in front of them. We did this over 9 hours on a 14.5 kilometer stretch of highway in Tennessee. And we would just collect all the radar data from that. And then rather than try to get the stuff to emerge from a simulator, we would just take either our car or the lead car, make it the leader in a trajectory, and then just put a bunch of human, AV, human, so behind it in the string. So the idea was that the AVs in this like mini simulator would try to smooth out the shock waves that were emanating from the car in front. And so this is somewhat calibrated by default. They say somewhat. The thing is, these waves are like extremely unrealistically severe, right? Because how the wave propagates here is going to be a function of the model of human driving. This is obviously like 10x speed, so it's not quite as bad as all that. But you have to make a choice about exactly how that wave is going to propagate through your system, and you do that by picking the human driver model behind it. Yeah, so the question is, what agent behaviors should we have for those little white cars? We picked a popular model, the intelligent driver model, which is a combination of it's this like parameterized model that's very popular in the literature with 4 terms. There's this pre-road term, which specifies how the car behaves in the absence of anything in front of it. It's going to try to speed up to basically V0. And then there's this interaction term that I didn't fully expand here that defines how the car interacts with just the car in front of it. And I'm going to use these throughout the talk, so I want to explain really quickly what this is. So if you take this driver model and you create that simulator that I was showing before, you get this time-space diagram on the top right. What we have here is time on the x-axis and position on the y-axis. And each line here is an individual trajectory of a car. So they're very smushed together, so you can't see that they're individual lines, but each one is a line. And the car that's replaying the trajectory that we got in the real world is at the front of this line. And as cars move through this, they're moving fast when they're green and slow when they're black. They hit the pattern of starting and stopping that's happening to the car in front of it, and then it propagates backwards throughout the system. So you can see these downward sloping lines are these stop and go waves that we kind of experience in the real world. Now maybe they vary in their angle or how severe they are in reality, but this is what we get when we replay it in the simulator. So the really important thing about this intelligent driver model is that you could pick parameters such that it is wave propagating rather than wave damping. We know that waves occur in the world. We know that they should propagate. Maybe they die out after some period of time, but we probably want them to propagate rather than just dying out. And this model has about 4 hyperparameters that you can pick however you want. And you could try to fit them to data, and default models of this are kind of fit to data in some way, but there was a lot of freedom in how we could pick these parameters. Also very troubling. The last thing in terms of agent behaviors is, if you saw, we had this kind of like 1-lane road. And the reason we had that 1-lane road is we didn't want to deal with lane changing models. So in reality, if we open up a big gap to the car in front of us, someone is probably going to merge into it, right? But this is just kind of a bit of domain knowledge. But there isn't exactly a lane change model that I would trust to correctly reproduce things. So we just decided we would throw it out and not use it in this 2-lane simulator. And that also has consequences. And these consequences are as follows. So the first thing is we don't trust our lane changing model. So we're going to insert some domain knowledge rewards. Our reward function is going to be something like negative of energy cost, because we want to minimize the energy consumed for a calibrated energy model. And then a penalty on excessive gaps. So we don't feel comfortable saying what happens if we open up too large of a gap to the car in front of us. So we're just not going to let our controller do that, right? So we're inserting domain knowledge saying, here's where we trust our models and here's where we don't. And the second kind of domain knowledge injection is that no weird controllers were allowed, where we define what that meant. In the sense that, when you do RL inside of a simulator, really weird things can happen. Like your little robot can discover that flipping lets it go as fast as possible. And you should say, okay, that's probably an artifact of the physics. Something's wrong there. And in the same way, we would periodically say, okay, well, it doesn't quite look like this is optimizing some kind of simulator artifact. Like, for example, maybe it's opening large gaps, closing gap really fast, opening a large gap, closing the gap really fast. We're going to say that's probably not something that we want. I'm not going to go into the details of the RL pipeline because it's not super informative, but we take this cost function, we stick it into our simulator, we do a bunch of RL with PPO, which is my favorite algorithm for many reasons. And at the end of that, 12 hours later, we have a controller that performs well according to our miles per gallon metrics. And in particular, the way we were evaluating it was this somewhat ad hoc way where we took 10 trajectories that we collected on the highway, so leader trajectories. We held them out during training, and we would run a sweep over 10 of them. And just say, however well we did on average across those 10, that's our metric for how we did. And we made sure that that had a mixture of free flow and congested traffic. So traffic where everyone was moving smoothly and traffic where everyone was moving in a congested way. One reason to include that free flow term in particular is because one of the easiest ways to minimize the energy consumption of your cars is to drive very, very slowly. And so you kind of want to watch out for that. So in this simulator, our human baseline, where we replaced all of the cars, had a fuel economy of 38 miles per gallon. And we did a ton of work building model-based baselines, kind of like PID type controllers and so on. And then at the bottom here, we have our RL controllers that, surprise, surprise, I'm going to claim we're better than all the other controllers. And these are what we put on the car.
So
yeah,
high is better?
high is good. High miles per gallon.
Oh, high miles per
Miles
gallon.
per gallon,
I thought
yeah,
this was like usage. I was like,
No, this is miles per gallon. Yeah.
Gallons per mile. I thought the punchline was gonna be it didn't work.
Gallons per mile. It's miles per gallon. Miles per gallon. Yeah, sorry, the punchline is this didn't work at all.
Don't try this.
You can kind of see what this does. The strategy is like very intuitive. So this is our fully human case. So this is another simulated trajectory. The cars open up like gaps in a particular way. They roughly keep, you can kind of see that as these like little white lines threaded through the thing. And you can see that they kind of like smear out the wave, which decreases the total amount of XL decel. So on net, it's an energy improvement, even though you can't get rid of the wave completely. I should add, if somebody wants to interrupt, I love taking questions. And oh, there is a question.
You add noise?
Huh?
You add
Oh, we definitely had noise. Yeah, for sure. These things are perturbed by some fairly large Gaussian noise. Which maybe that's not a good model of the noise in the system, but it is some noise. And yeah, what these controllers roughly do is they roughly keep a 2.7 second time distance to the car in front of them. That's the distance that it would take to reach the car in front of you if it was stopped. And then within that, they have particular behaviors around how they get to that distance, like how fast they speed into that distance and how hard they slow down to get to that time distance. So there's both a very intuitive strategy and then like a particular strategy on top of that. Okay, so large scale deployment. These are 100 Nissan Rogues sitting in a parking lot waiting to be put out for the day. I should add that the like actual RL controller design was spearheaded by Kathy Jang and Nathan Wiesler, who are two PhD students at Berkeley. And a huge team was involved in actually putting a Raspberry Pi into every one of these cars and like ensuring that they worked and fixing them when they broke and corralling all the drivers and just so many different pieces to this. So I'm really glad I didn't have to do any of that. Props to the people who did. So we take these cars out, run them back and forth on the I-24 every day for multiple hours over the course of 5 days. There were a couple of days where we had to stop for safety reasons, but besides that, we do that. And then we would measure the impact of these things. There's this awesome project called I-24 Motion, also from folks at Vanderbilt, where they placed 300 cameras over 4 miles that are just continually collecting data on these highways. If you're looking for a data set of people driving, this is definitely the biggest one that exists. It's all labeled for you. And yeah, so we were able to like kind of see our cars from top down and compute their MPG and as well as compute the MPG of the other cars. We had like not continuous, but pretty good tracking of cars. Okay, so results. I'm just gonna say that it was roughly a success on 2 metrics. 1, in terms of MPG. 2, we didn't hit anyone. The most important metric of them all. And the way that we're going to talk about measuring success of this is we're going to look at the MPG of cars as they are in terms of their distance to the AV. So how far they are from behind the AV. We can't influence cars in front of us, but we influence cars behind us. So we're going to look at, at 1 to 50 meters behind the AV, this is the fuel consumption. And as you move further away from the AV, the fuel consumption goes up, which kind of looks like a success. I'm going to have some caveats. But it kind of looks like if you're near the AV, you're getting some kind of smoothing effect. The challenge, of course, is that we have to think about yes, question.
I was also curious if you had any sort of how much like the variance,
Yeah,
variance was for these?
Huge. So here, in terms of like what the standard deviations are, I should include them, but I'm going to make the claim that they're small enough that these are significantly different.
Okay.
Yeah, the full paper I think should contain them, but it's a great point.
But
the other
second chart, the standard deviation.
Oh yeah, sorry, this is the standard deviation.
Yeah, so they also have
oh,
tighter
okay.
standard deviation.
Hmm?
They're also tighter as you get closer to the AV.
Yeah. So there's the decrease in the variance too, which
Yeah.
I think is indicative somewhat of wave dampening.
Yeah.
Yeah, it's right here.
Oh,
Great.
nice.
Why we didn't superimpose them, I don't know. How do we handle, so the other challenge is how do we handle counterfactuals, right? There are days where there are less waves on the road. And if we do a good job, there just are no waves at all. And then it looks like we didn't do anything. And there's also just like significant day-to-day variations in what the MPG of the roadway is. So you could try to fix this by doing like off policy evaluation or something like that, but that has really loose bounds. But this point I want to make is we don't trust our simulator to handle counterfactuals, right? So what we could do is we could take all the trajectories of all the cars we saw on the road, stick them into a simulator, complete them with some other drivers for all the cars that we don't see at any given time. And we just don't trust our simulator to do that. Like right now, our ground truth is whatever we got by driving. So takeaway, our success, I think we succeeded. I think that unfortunately we can't, because of this counterfactual issue, we cannot provide like absolute tight proof that we 100% improve the MPG of the highway, because we would need to do so many more trials than we possibly could do to do that. But we have kind of qualitative evidence of wave smoothing. We have this kind of increase in MPG as we move away from the car. But the other things I want to highlight is like, we couldn't just do this in simulators like we initially wanted. Data collection was needed. We didn't trust the lane changing model. We had to insert domain knowledge in the reward function. The eval procedure was fairly ad hoc. And again, we have to do real world tests at all to tell if we're making progress. If you look at the simulators themselves, you can get wild numbers of MPG improvements inside of simulators. Was that a hand in the back?
Yeah. Are there people that cut into your lane?
All the time, but less than you would think. Yeah, sorry, we're not controlling the highway. Like we're just driving on the highway. So if we open up a gap, people can cut in front of us, and they do. But much less than you would expect. So like there's kind of this intuition that if you open up an 80-meter gap, people are just going to cut in front of you over and over and over again, but they don't. There's some plots in the paper showing how often a gap happens, or a cut-in happens. So the point I want to make is we are limited by our simulators. There's a very roundabout way to make that point, but like 5 years later, I'm very convinced that we are limited by our simulators. So what I'm going to talk about for the rest of this time is about tools for building simulated agents so that we can have richer simulators that we trust and that we can use to do counterfactual evals and evaluate the safety of our agents and design new transportation systems and all that jazz. So the open challenge that we're focused on right now is the same one that kind of stemmed from that work. Where should behaviors come from in driving sims? And the first paradigm was the one that kind of in the transportation community is kind of dominant, is these like hand designed parametric models. Like if you look at a transportation simulator, it's got this intelligent driver model, and maybe has another model called like the Kesting model inside of it. And these are kind of these small models fit to a small amount of data. And the paradigm, if you look in the autonomous vehicle industry space, is learn a model of driving from big data sets, right? So we're going to do this either by supervised learning, so kind of just large scale trajectory prediction, or we're going to do this by imitation learning. So, just kind of behavior cloning, generative adversarial imitation learning, things like that. And I think there is some amount of evidence, and I've spent today suggesting to people that we should put some work into finding more evidence, that there's some limitations to this type of approach. So kind of the underlying model, at least in the AV space, is we're going to do the same thing we did for compute. We're going to collect a giant internet scale data set, which we do. So like if you're Tesla, you're driving, hundreds of thousands of cars around every day. You're collecting video from all those cars. You're also collecting action labels of people taking over the steering wheel and things like that. We're going to fit a model to that. That's going to be our human driver, or even the thing that we put on the autonomous vehicle. And I think the first challenge that I want to pose is that most driving data is extremely boring. It is just people driving in a straight line, almost asleep. Whereas internet data is extremely diverse. People care a lot about the thing that they encounter on the internet being fun and exciting and different. And so you get a lot of diversity that you just do not get by default. Rare incidents on the road are so rare. It's kind of in the name. Challenge 2, and this is more speculative and just something I just want to point out, is the largest scale behavioral cloning model that we know of in the world, pre-RLHF, is GPT-4, and it's extremely not robust. It makes mistakes all the time. And it is trained on more tokens than we have interesting driving tokens by a long shot. And so that one is much more speculative. You could sometimes people respond to that by saying, well, the space of all language is much more complex than the space of all trajectories, which I think is probably true. But the flip side of that is the set of rare scenarios that you encounter in driving are extremely rare. You almost never see them. You barely can collect data on them. And you certainly can't collect data on them unintentionally. I highly recommend spending some time on the Tesla Motors subreddit, just to see examples of the weird things that happen on the road. Like there's a video in there where there's a truck driving and the back of the truck is projecting what's in front of the truck. So Teslas will attempt to drive through the truck because they think there's no road there. I'm sure they fixed this at this point. I hope.
That's why we coyote that.
Yeah, it's exactly why. It's like somebody painted a tunnel in front of the Tesla. So I'm sure they fixed that problem because you see the problem, you fix it. I'm not certain how you fix that problem, but yeah, rare cases in driving are just totally wild. The other things I think are kind of some kind of interesting challenges are that it's not obvious that supervised models are learning what we want. So this is a really cool paper from some folks at Brain and Waymo called Causal Agents, a Robustness Benchmark for Motion Forecasting. What they do is they take a bunch of supervised scenarios and then they perturb them in a way that should not change the output. So over here we have this car, this is an AV, and in blue, we have the predictions of where this car might go next. So this is just like a big supervised model running, taking the scene and predicting where we're going to go. And in reality, the car takes a right? And we would think, because this is like an intersection, that at all times, given the position of this car right here, you would want to predict some probability of taking a left and some probability of taking a right. What they showed is that if you delete a bunch of these cars, the probability of taking a right disappears. And they have lots of examples of that. And these are models trained on fairly large data sets. So not clear that they're learning what we want. There's some valid criticisms of this paper. I don't have time to get into them, but I think there's valid takeaways from this paper. It's a good paper. The second thing is that if we look at these supervised models, which should be learning to drive coherently with each other after training on thousands of hours of data, and we look at their collision rates in closed loop and their rates of going off-road in closed loop. So we take our supervised model, our imitation model, we place that on every car, we set up a scene, and then we ask them to all drive to some specified destinations. And we look at their collision rates. So here, going up means low collisions. So 1 means no collisions, 0 means collides all the time. We look at their collision rates and their off-road rates on the Waymo Open Sim Agent Challenge. The best models there crash around 10% of the time and go off the road about 10% of the time in closed loop. And these are 8-second snippets. This is not long coherent driving. These are little short driving snippets. And if you're thinking about using these agents for evaluation or in a validation set or something like that, then I don't know how you use models that crash so often. And in particular, if you ever talk to an engineer, and they give you a new controller and you run it on your validation set, they will come back to you and say, I didn't mess up. The simulated agents did. Like, this is not my fault. Like, go back and fix your validation set. Of course, it's possible that this is all resolved by scaling. It's always a possibility, but yeah.
Isn't this also a consequence of the fact that like all of these prediction agents just spit out top 5 like estimates instead of having like a distribution? And is there like sampling, digitization or discretization that's going on
Over here?
Yeah, right. All of these agents, they're
all outputting distributions. Yeah.
I mean, aren't they like top 5 trajectories?
Yeah.
Which is a way of sampling from a distribution.
Yes.
I guess my point is instead of doing 5, right, you don't run your Eugene particle filter for your 2D robot with 5.
Yeah, I think they do 32 or something
Do
like
they?
that. Yeah.
Okay.
But yeah, or maybe it's 5. I don't know quite.
I think
remember.
like,
But you mean is that you could filter out the trajectories that don't crash?
well, I guess my point is like, they're trained to do 5 bites at the apple because that's how they're
Yeah.
evaluated, but like that seems suboptimal if you wanted to roll these out over long horizons. Right, because you know, you repeatedly take 5 bites at the apple, you're maybe getting mean estimates, but you have way higher variance.
That's true. That's true. I'm not 100% certain whether this is the collision rate of like rolling out all the trajectories and taking the best one or something like that, or
Yeah, it's probably like the most confident or something. I mean, I've also, yeah, they like drive off the road.
they drive on
These are-
if
they're
you play with
bad.
that, they drive off the road all the time.
They're bad, but like,
Yeah.
I wonder whether this isn't just a consequence of like the problem formulation they're trained on, which is they get 5
Just
bites at
getting,
the
yeah,
apple. Because they're rewarded by the closest of the 5 trajectories.
yes.
Ranked by confidence,
Mhm.
which, right, you really want some sort of like true like distributional understanding that you can carry forward.
Yeah, I mean, I think there's certainly ways to refine these agents to like boost up their collision rate if the thing you were doing was not trying to like distribution match
Yeah,
to like to satisfy the actual objective of this problem. There's a question there.
And to extend on that, I mean, obviously there's a grossly asymmetric cost of error, so you don't want your best trajectory at all.
Yeah.
You want the one that avoids the probability.
Yeah, and I mean, these challenges also like require you to crash some percentage of the time.
Really?
I one thing, yeah, because like you're trying to match the expert trajectories, and the expert trajectories in these data sets have crashed because of noise in the bounding boxes.
oh, I see.
Yeah, so they have like by default have a 2% crash rate or something like that.
Is that what the log oracle is?
Yeah, but here I don't understand how they get
0?
100% here because I know for a fact this data set has crashes in it. Yeah.
The Waymo,
Waymo open motion data set.
okay.
Really cool data set, but like it has crashes.
It's BEV
Fake
bounding
crashes.
boxes,
Huh?
right?
Yeah. I mean, they have extracted post-perceptual trajectories, but
Yeah.
they also have the bounding boxes for each one. It's a cool data set. Really great. Really glad when a company releases some data. So I want to, here's a giant picture of my grad student. So what I'm going to talk about, because I'm a man of one hammer, is how we can resolve these problems with reinforcement learning. So here's what I'm going to claim. I'm going to claim that self-play reinforcement learning is a great solution to this problem for building agents that are really capable in closed loop, but also kind of reflect the diversity of behaviors that we actually see on the roadway. So both closed loop capability and distribution matching. So self-play reinforcement learning has been a dominant tool at building agents in zero-sum games. That's not true for every zero-sum game. Like poker is solved with non-RL methods, but Stratego was solved with RL methods. Diplomacy was solved with RL methods. So it's a mixture of RL and non-RL based things. But it's great at solving zero-sum games. It's great at solving cooperative games. It really in this self-play setting, we know how to build superhuman agents by self-play in a lot of cases. And so what we're going to do is we built the simulator Nocturne. So some folks at Facebook AI Research and I built this a couple of years ago. It has support for expert replay. So every car here is a trajectory taken from the Waymo motion dataset, and their colors correspond to the goal that they're trying to get to. So this blue car is trying to get to its goal here. And on the right, we're trying to model humans, not AVs. So we kind of have the perceptual abilities. Each car comes with the perceptual abilities that a human with 2 eyes mounted on a head would have. So they can't see through cars too well. There's a lot of partial observability, and in fact they have to turn their heads to like see more information about the world, which we thought would be really fun because it means you could get kind of emergent agent behaviors like agents making eye contact to confirm that they see each other before proceeding on their way. Haven't had a chance to do that, but I think it'd be really fun because it is something that humans do to coordinate between cars and pedestrians. Okay, so we set up self-play in Nocturne, which is our beloved driving simulator. Each agent knows the goal that it's going to get to, but does not know the goal of all the other agents. So it is operating under some partial observability, both in its ability to see and in, where the other agents would like to go. We set up self-play in this, and we get a result that's really good on crash rate. We can get it to 100% closed loop performance, so like 0 crashes across all the scenes that we encounter. But when we look at this, so we're having the view tilt with the agent, and this is bad enough, but what comes next is just so much worse. So it's good on closed loop. It's not great on the human likeness aspect. So the issue here is that we would like to make self-play controllable. So the thing is, self-play can build human-like, human level, and sometimes superhuman level policies, but in any many player game and any non-zero sum game, or almost all many player games and almost all non-zero sum games, there are many equilibria. These equilibria are not compatible. So if I train agents in self-play and I take the equilibrium that they learn, train agents in another run of self-play, and I take agents from that equilibrium and I pair them with each other, they will no longer be superhuman. So this is the problem of like equilibrium selection. This is not true in 2-player zero-sum games, which is why they're so nice sometimes. And like a very like natural example of that in driving is like, if you run self-play, sometimes the agents will learn to drive on the right side of the road, and sometimes they will learn to drive on the left side of the road. And there's nothing a priori shaping that unless you stick it into your reward function. We don't want to do that. So the question we've been asking is how to actually shape equilibrium selection so that it converges to an equilibrium that satisfies some properties that we'd like without actually going and specifying it in terms of the reward function. Don't like that. And so I've been calling this guided self-play. And the idea is that we're going to take some sound self-play algorithms and we're going to fuse them with demonstrations or preferences from humans or a human in the loop and figure out how to like try to shape the equilibrium towards an equilibrium that satisfies some desiderata that we have. So what I'm going to talk about is kind of an instantiation of this. So if you think of driving as like a goal-reaching game, then there are many effective goal-reaching policies. For example, cars that drive on the left side of the road and cars that drive on the right. But there are, additional things that you could have on top of that. And within that, we're going to say that humans play a particular policy from the set of equilibria. And then we're going to have many other equilibria that are unlikely under data collected from humans. And the idea here is that driving is like mostly about capable coordination, like, reasoning about the fact there's a car to your left, you should maybe give it a little berth because it might turn right, things like that. And then on top of that, some like preferences over how we interact with each other. And we're going to try to use data to shape that equilibrium selection procedure. And so the hypothesis is that most of driving capabilities are going to emerge from game solving. And then we're just going to try to get conventions, preferences, understanding of the limitations, of like actuation limitations and like kind of rationality limitations from the data. And kind of an underlying thesis that's maybe a little bit unstated is that there are just like not that many effective ways to drive. There's mostly just good driving, then there's like a little cherry on top of that. This is not a new idea. I just want to be clear because it would be wrong to claim that I had come up with this. This KL regularized self-play is like is an old and common idea. And in particular, as kind of some prior evidence that it works really, really well for guiding equilibrium selection, we can kind of look to diplomacy work from FAIR. So diplomacy is a multiplayer strategic zero-sum game. Because it's multiplayer, it empirically has been shown to have an equilibrium selection problem. You run self-play, you get an agent, you pair that with humans destroy the agent. Like that agent does not do well against humans at all because humans are playing some other equilibrium. Maybe they're not playing it as well as self-play agents would play that equilibrium, but it's not compatible with the equilibrium you recover from self-play. And the idea here is that they got human level performance through IL regularization. So they took a small amount of diplomacy data They learned policy through behavior cloning, just imitating the labels on that data. And then they added that as a regularization term to the normal self-play objective. And by doing that, they got superhuman performance in no-press diplomacy, which is without language. And then they similarly got superhuman performance in diplomacy with language by kind of adding an LLM on top of that and doing some other clever things. And I think this is like a remarkable and I think possibly underappreciated result that like all they had to do to get this to work was just like collect a little bit of data and do regularization on top of that. Because in principle, this does not work. In principle, adding a Kale regularizer introduces new equilibria to the problem that didn't exist before. And so first of all, maybe those are the equilibria you want to play. But you know, it's just kind of marvelous that it works, that it worked. I thought this, I've been obsessed with this since it came out. And so we're going to kind of do the same thing. We're going to, we formulated something we call human regularized PPO. So we're going to do self-play PPO, and then we're going to add a Kale regularizer for our policy pi theta against some policy tau, where tau is going to be learned through behavior cloning. So imitation of the of data collected from Waymo. And we're going to use an exceedingly simple reward function, very on purpose. So our reward function is going to be 1 if the agent reaches its goal and 0 otherwise. And the reason we're doing that, no other shaping, is because we do not want any of the behavior, of the coordination behavior to come out of our reward function, right? We don't want to say, okay, it's in the lane center because we stuck that reward function in there. We don't want to say it stops at stop signs because we stuck that in the reward function. I mean, you should probably stick laws in the reward function, but separate thing. So no reward shaping. Okay, details. So we take our like a bunch of scenes from Nocturne, which are just like kind of taken from the Waymo data set. We use initializations from the Waymo data set to initialize our scenes. And then we give the agents goals that are the terminal position of agents in that scene. We pre-trained a 50% goal rate behavior cloning model, which to be clear is a bad model. Like that is extremely bad goal reaching behavior. And we do that on about 30 minutes of data. So that behavior cloning model is trained on 30 minutes of human driving data, but human driving data in multi-agent settings. So what happens when we do this? So we want to evaluate 2 qualities of the subsequent model. 1, is it human-like? And then 2, is it human compatible? Meaning, does it drive well with humans? Like, are we shaping behavior toward the equilibrium that we intended to shape it towards? And my student is very good at drawing, Daphne is really good at drawing cartoons. So they're going to be cartoons. So there are 2 realism metrics that we use for measuring resemblance to data. The first is ADE, which is kind of a trajectory distance error. So at each point along the expert trajectory, we take our trajectory that we actually took and we compute a distance to it, and then we average over that. And the second is action differences, because you can have 2 trajectories that are quite similar, but the car wobbles the whole way along the way, and it would be terrifying to be inside of, but it wouldn't show up in the trajectory. And I want to add like one refinement. So instead of the ADE, we're gonna compute something called the GCADE, which is we call it the goal conditioned ADE, because unlike normal trajectory prediction, we actually know what the agent's goal is, which is something that you normally have to infer during supervised trajectory prediction. So we don't want to mix things up by using the same term. And what we see there, so in the bottom left, we have the behavior cloned agent, 50% goal rate, but really low GCADE. And to be clear, this is like a little artificially low because we terminate the computation of the ADE when a collision happens, because we don't know what to do after that. So this would actually probably be a little higher in reality. And then we have our HR PPO agents at different levels of regularization. And you can see they kind of sweep at this Pareto frontier where we can get, but the nice thing is we can get these agents that are pretty good on GCADE, but have fairly high goal reaching rates. Note that here we're only reaching a goal reaching rate of 92%. Part of that is because we're regularizing to an imitation model that wants to crash. And so unavoidably, there is some non-zero probability of taking one of those bad actions. So better BC models would give us higher goal rates. And the second thing is we actually had to stop trading at some point because this learn cluster kicked us off. So I'm going to talk about that at the end, what we do about that. In terms of steering, it is extremely similar. So we're going to usually use this this lambda equals 0.6 model over here, which is almost identical average steering error. Yes, question.
Have you tried scheduling this lambda factor?
Yes.
It seems that, it would make sense to nudge it into the right direction in the beginning, and then once it's, so to say, in the correct local
Yeah.
vicinity of the equilibrium that you're looking for, at that point, you just like have the.
Yeah, so you could consider, it's a great question. You can consider annealing lambda down and then just like converging towards the basin. And you can come up with theoretical descriptions of this that show that like under some conditions, annealing off lambda would cause you to converge to the basin of the equilibrium from which you had sampled the data. But there's two problems here. So one is our reward function is not actually the human reward function. So like on top of just having arbitrary preferences over what each equilibria plays, we also like don't have a term for stopping at a stop sign. And if you anneal it off, they will stop stopping at stop signs. That's not like that's not a stable equilibrium.
Yeah, okay, I see, roundabout.
Yeah, or roundabouts. But if you added more terms to the reward function to like get some of those laws in there, then I think you could anneal lambda.
Yeah, I was just wondering if that would happen. I guess.
It definitely will. They absolutely will stop stopping at stop signs. Yeah.
Why is game theory why are humans driving according to a game theory?
I don't think they're driving according to a game theoretic optimum. Well, the claim is that they're driving according to a perturbed game theoretic optimum. So the Kähler regularization does no longer corresponds to like a particular Nash equilibrium. It could possibly include things like you should behave irrationally with some fraction of the time, right? So it's not exactly saying that humans are acting game theoretically optimal.
But I mean, it's sort of trying to do that, like the learning is trying to find at least the parallel.
Yeah, but it is trying to do so with respect to a Kähler regularized equilibrium, which is not the same original equilibrium.
But it's like, why is, I mean, when we think of driving, okay, maybe we're doing game theory 1%, maybe 0.5% of the time when we're actually driving. Other times we're just sort of falling along and then trying to speed up and slow down according to our neighbors.
Yeah.
Yeah.
Well, so I think there's nothing that prevents the Kähler regularizer from causing that type of behavior to occur. And B, there's no sense in which driving behind another agent and driving straight is not driving like game theoretically optimal. It's just at that moment you just need to go straight for a while. But I think it's a good question.
As a control, could you look at driving in, say, the UK to see if you learn that opposite?
That's a great experiment. Yeah, I love that. I mean, I think we will, but because that part of which side of the road should you stay on is like very easy to pick up. Like the other conventions are more nuanced than that, but also we don't have a data set from the UK. But we do have data sets from different cities, so we could consider like looking at like local goals and behaviors in the cities. Yes.
So the regularization objective is on the actions that is suggested by a BC policy.
It's with respect to the distribution of the BC policy.
So when you're creating this BC policy, it's often out of distribution to what
Yeah.
it has seen.
Yep, totally.
So how would this regularizer kind of behave in certain scenarios?
Right. So to some degree, we would like that's part of the thing is it causes us to like try to take bad actions because we're regularizing towards it. So there's a couple things you could do. One, instead of regularizing to a bad BC policy, you could just regularize towards the data itself. Right, just continually stick the behavior cloning loss in on data sampled from the expert distribution. You could consider making lambda dependent upon like some kind of uncertainty quantification of if you're out of distribution or not for the BC policy. But the other thing is the RL partially compensates for the BC policy making bad suggestions. So you could imagine that if you had quite a good BC policy in the first place, the RL would just compensate for whenever it was making really bad suggestions. Yeah.
So is the moral of the story here that you can have okay, but not great BC? RL will do the heavy lifting and you'll get super BC human level performance.
I think, well, specifically, we want human level performance, but not superhuman level performance, because we want these to be simulated actors in the simulator. But I also don't want to make that claim specifically. I think we're providing some evidence towards that being true, but not that that is true.
Sure.
But that is the claim we're trying to build evidence towards.
Okay, and that's contrary to what most people do, which is they throw BC at it and then maybe tune.
Yeah, so it's kind of flipped, right? We're doing RL with little BC on top instead of BC with little RL on top.
Yeah.
So the second measure that we started with is like our agents should be closed loop, low crash rate. And we're not 100% there yet, again, partially because of training issues rather than anything particularly wrong with the method. Like we can see our curves going up and then the Slurm cluster kicking us off. But so in closed loop over here, we have self-play. So in self-play, every agent is a copy of the same policy. They're still under the setting where they don't know each other's goals, but they're doing kind of closed loop driving behavior. Our BC agent here is at 50%. Our PPO agent is like around 95%, 93% or something. And we can see that our regularized agent just matches that in self-play. But then when we move to log replay, which is our current proxy for human likeness, because we can't put our cars on the road and drive them around with people yet, where we have one agent controlled and all the other agents non-reactively replay their data. So this is a common way of measuring human compatibility. You could imagine better things, and we're trying to build towards those, but that's what we have right now. And there we see a 50% improvement over this proxy for human likeness. So PPO in this log replay mode drops down to, I don't know, 70%, and there's like a 15% diff here. And that doesn't sound like a big diff, but it actually is. And the reason it is a big diff is because almost 70% of scenes are just straight driving. So it underrates like what our agent is doing in complicated interactive scenarios. So we have this like proxy measure for interactivity, which we call the number of intersecting paths. We just look at the expert trajectories. We kind of time window them and look at how many of them cross in a given time window. It's just a proxy measure for interactivity. But as we go up along that, we see that the PPO agent starts to crash a ton in those more interactive scenarios in log replay, whereas our agent in orange kind of stays somewhat flat the whole way through. So we get a really big improvement in the most interactive scenes. And if you kind of look at this previous, no, it's backwards. Okay. So this is the scene I showed you from before. This is that same scene replayed with our agents. It's getting a little closer than I would like.
Okay.
Yeah. Yay. And then kind of in log replay, where here our car is in red and every other car in gray is doing log replay, you kind of see that the pure self-play agent kind of expects the other car to swerve out of the way because that's what it would have done in its equilibrium. And whereas our agent just like nicely waits, but a gentle driver. Okay, so what I talked about, I need to make their faces smaller. Is that we started to run into this issue where we were running out of our 2-day time budget to run these experiments because RL can be pretty slow. And so what we've been working about is like finding good ways to scale this up. Nocturne, the simulator that we built, runs at 6,000 frames per second, which is actually pretty fast. We spent a lot of time optimizing it. We wrote it in C++. We optimized like instruction sets per CPU types, all sorts of weird stuff. But the best self-play policies occur in billions of steps. That's just like, looking at results from DeepMind, that's what you see. But in recent years, RL has been accelerated by tools like JaxMarl, Jumanji, Isaac Jim, Waymax. These are all batch simulators that run on GPU. And in particular, Waymax is actually a driving simulator released by Waymo. That's really great. But instead of using Waymax, we built our own version that has some advantages and some disadvantages relative to Waymo that make it useful in some cases and annoying in others. This simulator is creatively called GPU Drive. I'm not great at naming things. It is a 2.5D multi-agent driving simulator. It runs at, on every GPU we've looked at, roughly 1 million FPS, which it can be as low as 750,000 FPS and as high as 3.5 million FPS, depending on some criterion. So blue is this like the idealized version of the scaling curve as we increase the number of different environments running on the GPU. So we go from 0.5 to 3.5. Orange is what we actually get right now. And the reason that this is so different is because we have all these like fake padding agents that handle the fact that there are different numbers of agents in each environment. And currently we're computing observations and actions for those fake padding agents. So as soon as we fix that, this curve will become that curve. But just wanted to be honest about what we have here. Some nice things are that it's really straightforward to write complex observations in it. So like we have a LiDAR space inside of it. So you can like simulate LiDAR, you can construct whatever observations you want. It's built atop the Madrona engine, which is this really wonderful work from Keyvan Fedahalian and Brennan Shacklet at Stanford. If you want to write GPU sims, I highly recommend looking into it. It's awesome. The way Madrona works is it's a C++ to CUDA transpiler, which means that writing new features is easy if you think that writing new features in C++ is easy. So it's really easy to add scripted agents, add new observation spaces, whereas you can write those things in JAX by writing all of your operations as batched operations in JAX. But that can be really hard for some people. And there are many operations that are hard to express as fully JITable operations in JAX. It takes a lot of like practice and expertise to do. So in some sense, we think this will enable like people to build new features atop it somewhat straightforward, which I think a lot of the appeal of it. It's also fast. So to finish this up, here's a huge list of collaborators that contributed to this work, a huge number of advisors, a very large number of companies that contributed to that like 100 vehicle deployment. And then I also want to thank the Emerge Lab, which is the name of our group at NYU. There's some of my PhD students, master's students, and undergrads. They're all great. And then I have to do a required plug before I go. We started a new RL conference. Again, because we're bad at naming things, it's called RLC, the Reinforcement Learning Conference. It's at Amherst, August 9th to 12th. The deadline has passed, but there are a ton of workshops that are going to be announced this week if you want to use that as a reason to come. And if you come, you can find out things such as, what is David Silver up to now? What is he doing? And many of our other excellent keynote speakers. So with that, thank you. If you have any questions. Yes.
Film was originally 24 frames per second, and yet you could still tell quite a lot from it as a human. Do you think that you could learn a lot at very low frame rates per second, maybe having models that keep on doubling the frame rate per second, and see how far you can get before you get diminishing marginal returns? Or stay in competition?
Yes. Yeah, I think training agents at different timescales is an extremely good way to speed up the efficiency of these things. Yeah, and in fact, it does speed up training if you first train at like 1 hertz, then 4 hertz, then 10 hertz. And a lot of self-driving stacks run at about 10 hertz, but some of them do run at about 100 hertz. So.
But so why did they come up with the 1 million or the billion? Or
oh, but that's how fast we want our simulator to run. Like that's total steps of experience
so
generated by our simulator. So there's like 1 million or steps that you can train your RL algorithm on every second. It's not the actual frame rate of the simulator, in case that was the.
Well, in other words, so the simulator is, the frame rate is the simulation of the frame rate of time.
It's the number, this is why frame rate is a bad use, and I sometimes call this agent frame rate. It's the number of steps of experience generated for the agents. So it's the number of observation action reward pairs generated per second.
So that includes multiple modalities, essentially.
It includes like this kind of like LiDAR observation space, and then the actions and the rewards. Yeah. If that's what you mean by modality.
Well, just the human would not have any sort of frame rate approaching.
No, but individual environments in the simulator don't actually run that fast. It's the collective, like 300 agents over 300 GPU worlds running that fast. Yeah.
That's the most related question. I'm just curious if you've learned anything surprising or interesting about human driving behavior by looking through all the data. And for example, like, is there a huge variance in behavior between different geographical areas or interesting things that you've seen?
Yeah, so I haven't seen that in this data set, but there are huge variations in human driving behavior between countries, between cities. So like, for example, like shockwaves, like these traffic shockwaves I'm talking about propagate at different speeds in China and the US. So just like as an example of things that happen like that. But I haven't seen that by looking at this data. They're just things people have studied in other settings and demonstrated.
Anything just like strange or interesting you learned about human driving behavior? In particular?
I mean, I've certainly learned that humans do a lot of weird things by watching different videos from self-driving car companies. I mean, you.
So, yeah, I mean, from this, right, you had like a mediocre PC model.
Yeah.
Do you think the move, big picture, is to like get a better PC model, hit a better regularizer, and then just do it from self-play, and that's
Yeah.
how you get really high quality, long tail handling policies?
I hope so. That's definitely the next thing we're gonna do.
Okay.
Yeah, it's a very straightforward path. Like, we're doing this with BC, we should be doing this with something like Gale or just like a better IL method. There's a lot of work to be done in cleaning the data. The data in the Waymo data set has some oddities in it that require some cleaning up.
And is this just because the bounding box based like tracking that they have?
No, I mean, it's partially something we haven't quite been able to figure out, but like to get actions, you need to invert the kinematics model. And we haven't been able to find a kinematics model that, like when we invert the action, that when we take a trajectory and we invert the kinematics model and compute the label, the actions, and we replay those actions, we get a pretty high crash rate. So we're not even generating like action labels that are giving good trajectories.
Is it possible they have like a heterogeneous fleet and that's why?
I think their fleet is not that heterogeneous. But I do think that the kinematics model that we're inverting is not quite correct.
I see.
And the second thing is that technically with the models we're using the same model that's in Waymax, but you need to match three things. You need to match heading, X and Y.
Yeah.
But that model only has two actions, so it's here in Excel, so you can only match two objects in the trajectory, and we're not like matching the right mixture or something. Like we're just matching position and not heading. We're heading and.
I imagine the heading is because the detectors are a bit noisy.
Yeah, I think that's a piece of it too. Yeah, so there's just some basic work to be done on. Should I give Eugene control of my screen?
Sure.
Hi, Eugene. How do I give her control of my screen?
Is there?
Speaker right here. Is there a question in the chat? I don't. Oh, would people in the chat speak through that, or how does that?
Yeah, if you unmute, they should be able to come through here.
But if I unmute, then you guys are gonna hear.
No, I think it's.
No, there's a mic here.
This is fine, because we just heard.
Yeah.
Okay, just.
Okay.
Yeah, you're, how it's set up right now is how.
Okay. I want to just mute. We're all discovering that I don't understand how technology works.
No, you don't have to do anything.
I don't have to do anything.
Yeah,
Okay, cool.
they can hear us.
Okay.
They should.
We have some questions.
So if the goal is to build something that can drive.
Yeah.
Why don't we use the RL agent that works and doesn't crash
Yeah.
and forbid the humans to drive? If all the cars use the RL agents, then we have a policy that works.
Yeah. My opinions on driving are controversial and should not be stated in a public forum.
Okay.
Yeah.
Why is the RL goal being like going through a specific goal?
Yeah.
Reasonable future.
I mean, we have to give the agent some task, right?
Yeah.
So the task, I feel the task of getting to a particular goal by some time is a pretty clear descriptor of what happens with driving. You want to get somewhere eventually. What would be an alternative?
I mean.
NBC
Not
to
a
the goal.
specific point, right? Like maybe going to some lane, for example, but.
Sure, but you can phrase that in a goal language. Like, you can make that a sequence of goals, right?
Yeah, I guess, but it seems when we drive, we have a goal in mind, but our goal is sort of far away.
Yeah,
Not-
so,
not-
I mean, our goal is eventually to give the agent a goal that's a mile away and just say, go there generically. Right, the fact that these scenes are short is because the Waymo maps are small. So we can't give it a goal that's a mile away, so we need to start working on like integrating this with like large scale maps. But since the goal is really about like agent interaction and not like 10-minute drive, we're not trying to build a driver yet.
Right.
We're just trying to build the background population that can be used to evaluate a driver. And so we mostly care about these like short interactions right now. But you could just give it a goal a mile away and ask it to go there.
Yeah, towards the goal of scaling up, is there a case where, maybe said you mentioned, right, there's certain rare events that are maybe more informative or more useful in driving, right? Is a case for scaling up to, prioritize the data that you train on, or is there some sort of data selection process that could aid in this, more efficient learning where, maybe a lot of the interactions or scenarios are fairly simple then?
Yeah, I think once we start getting pretty good at this, like, I think then at that point, we can start maybe simulating really rare scenarios and like looking at the behavior in those cases, like start constructing synthetic scenarios that are deeply weird. But right now, if we take these cars and place them in deeply weird synthetic scenarios, they'll just crash into each other. So, I mean, that's part of the agenda of scale.
I guess, you could view it as an aggressive driver avoidance problem.
Yeah.
So I guess, Thomas Schelling, who looked at cooperative games a long time ago, kind of, thought of an idea of danger chess, where losing is bad, but there's something that's a lot worse than losing. He was looking at the case of nuclear war, but so in this case, not getting to your lane is bad.
Yeah.
You failed your goal.
Yeah.
But crashing is a lot worse than that.
Right, so sorry, there's a hierarchy of rewards here. The agents would prefer not to get to like, we can add a tiny penalty for collision such that agents would prefer to idle rather than,
Why a tiny penalty?
I mean, you can make it a big one if you want.
I mean,
I think with the idea is that even adding a tiny penalty will cause the agent to prefer idling versus not getting to its goal.
that would be realistic.
Yeah.
And I mean, you could have a couple of drivers in there who are aggressive, but in other words, it just seems to me like the goal is generally to avoid, I mean, for most people, is not to get to your lane in the most optimal amount of time, but to avoid the a-hole who might basically,
Yeah, that's a good point. We're gonna add a collision penalty at some point.
So, I mean, I understand not wanting to do BC in the context of wanting to reach superhuman performance, right? You want to be able to explore.
I think, or even human level, but
Sure. Well, I guess the follow-up question was, why not just do BC for this, where you do just want human level?
right, because so far BC has not been able to give us 100% closed loop goal reaching rates.
And you're basing that off of trying to do the trajectory predictive rollouts.
I'm basing that off of the trajectory predicted rollouts, other works in imitation learning. So like there are a lot of groups doing imitation learning for building like human-like drivers, and they do not yet achieve good closed loop rates that are comparable to what you can get by just running self-learning. So I don't know what the limitation there is. I don't, I'm
I will
not,
compare it against non-learning solutions.
I think against non-learning solutions also struggle to get non-zero closed loop collision rates. Or when they do get when they do get zero closed loop collision rates, they, don't reach their goals necessarily. The other thing is, in terms of non-learning based solutions, I haven't seen those methods benchmarked on like over thousands and thousands of scenes. They tend to be benchmarked on like a couple examples. I would really love to see some like non-learning based
Yeah,
methods,
you
like
can.
really.
Can you comment? Can you comment?
Yeah, they run for a long time, maybe 4 minutes for an 8-second
Okay,
scenario.
Wait, why are they so expensive? They're not learning based.
Oh, yeah.
Well, game theory, output control line.
I see.
so I would like to see those methods scaled up because I'm very curious how they perform, even if they're expensive. One nice thing is, we have these fast simulators now, so maybe you could like parallelize the computation across different environments. maybe scale up in that way. Yeah, I'm very curious how non-learning based methods perform at scale in these. On this problem.
Do you think the failure of BC is BC, not the like surrounding problems you're also running into?
Yeah, so I think when like Waymo releases papers, they're not having the same problems that we have, that we're running into, because they figured out the thing that we haven't figured out yet.
Sure, they have the proper car model for their car.
Yeah, and they still do not get, 100% closed loop performance from IL based methods. I mean, be cautious, maybe they're gonna drop a paper tomorrow.
Sure.
We saw your grasp talk, that wasn't true.
Are they like within spitting distance? I guess I.
Yeah, it's like 98%.
Okay,
I actually don't know what the scores are in closed loop. That's in single agent control against logic play.
but how much of that is because it's world on rails and like,
Well, the other cars are on rails, you're not.
yeah, but like, I think it's, if you do BC where your logs assume that other people react and then you get deployed in a world where they don't react, like there
Yeah.
is a distributional shift.
I agree, but then you would check that by doing the closed loop thing where you place your BC agent on every car.
Sure.
Like how they do.
And then they
And
don't.
I've been trying to find this paper again, but I'm pretty sure they don't do super great. I think I've definitely seen some benchmarks where they don't perform super great, and I wish I had like that paper to point to.